This is the August 2022 real analysis portion of the qualifying exam that I took. I do not have a copy of the complex analysis portion, although both of these parts are available on the university website in the public domain, so anyone can look this up. But this is the test that me and my peers took, and it's the one that absolutely bodied me when I took it. And you can see it's really wrinkled because it was in my backpack just floating around for like a semester, so it got all wrinkled. But here it is, you can read what the problems are. So I thought I would show it to you. The first question is always a theorem, and the theorem was prove the monotone class lemma. The monotone class lemma says that the least monotone class containing a ring coincides with the least sigma algebra containing the ring, provided that the whole space can be represented as a countable union of ring elements. The monotone class lemma doesn't really appear much, I think, in literature like this, or at least not in the literature that I have. I'm not saying that it's like an obscure theorem or anything, but I don't really distinctly remember it. So when I took this test and I was practicing the theorems, it slipped through the cracks. So I did not correctly prove the monotone class lemma. It was kind of like nested inside another theorem, and I don't remember what the theorem was. But anyway, so the other problems we can take a look at. Question 2 says, does there exist a locally finite but not identically zero non-negative Borel measurable function mu, or a Borel measure mu, such that for every two real numbers a less than b, we have the following conditions. The measure of the interval is less than the length of the interval raised to the 2022 power, and then the same thing but the reverse inequality. A and B are two separate questions. Number 2, I feel like was in my capability had I studied my notes more. It's just in the past I've noticed that problem solving tends to be more useful than studying notes, which was the case for that test I took in the yellow folder from about 2 weeks ago. But in this case, this was mostly, I think, notes. I think had I studied the notes more, I would have done better. All right, what does the third problem say? Let Fn be a sequence of Borel measurable functions. They're on the square, 0, 1 to 0, 1. They tend to 0 almost everywhere. Show that the sequence of Hardy-Littlewood maximal functions also tends to 0 almost everywhere. And then he gives 2 hints. The first hint says, generalize the statement to the case where F1's bigger than F2, bigger than F3, so on and so forth. The weak type 1-to-1 estimate may be useful. I believe hint number 1 was how he expected us to solve it, but he showed this test to some colleague of his, and he suggested a different way to do number 3, which inspired hint number 2. Hint number 2 says, you are not obliged to use hint number 1. I thought that was kind of funny. Hint number 1, here's how I want you to do it. Hint 2, you can do it your way if you want. So I thought that was funny. Question 4, show that the improper integral converges and is positive. So that's his calculus problem he likes to put on here. I was a bit embarrassed that I did not get number 4 correct, because it is kind of easy when you look at the solution. I'm kind of embarrassed that I wasn't able to do it. It's different when you're under the clock, right? It's the difference between shooting baskets on the basketball court without the, clock on you, and versus when you're playing a game, where the time does matter and the shots do count. I like it to that reason. So if I had to give some advice if you're preparing for a qual, I would say, what would I say? I would say that try and mimic game day conditions as best you can. Because when you're sitting there taking the test and you have the clock on you and every stroke of the pen matters, you don't want to let the nerves get to you, because then you start doing weird stuff. Because my original intuition for this problem during test day was correct. It's just I talked myself out of it. and I wish I really hadn't done that. So, something to keep in mind. And then number 5 I just didn't care for. I don't like number 5. Show the double integral converges on the square if and only if the double integral converges on the half square, roughly speaking. I think the f of x squared y just confuses me. I've seen the solution to this and I still am a bit shaky on parts. I know it's not the hardest problem, but for me it was. I know that when we went over the solutions to this test, he believed number 3 was the toughest, but the one I spent the most time, well, okay, I spent a lot of time on all of these, but the one where it's like I just really didn't know where to start was number 5. And I know it's a push forward solution. I knew that's what I needed to do. It's just I didn't know how to really write it down. You know, the one direction's obvious, right? If you converge on the whole square, you converge on the half square. But going the other direction was strange for me. So in hindsight, I guess, well, at the time, I don't think I was prepared to pass this test. Even though I spent like hours and hours every day for like 8 months straight preparing for this test, I still don't really think it mattered. I think I got the same score had I not studied at all, which is kind of depressing to think about. But I took this in August, and it's February now, and I'm better at analysis now than I was when I took it. So hopefully in August of this year, when I take it again, I'll be even better. So that, and you know, it's also like luck of the draw almost. You know, you got to practice the problems, and hopefully something will show up that is something that resembles something you practice, because I don't really think there was much on, like this trick that's used in number 3, I don't think I practiced too much. This one was the reason, because these 2 I missed because I didn't look at my notes. 3 was, I could see like half of 3, but the other half not so much. Number 4 was just me being stupid, and number 5 was me being stupid. So I think that if I just prepare every single day and memorize the tricks, accumulate the most tricks that you can. Analysis is kind of a game of tricks. You know, what do you know that can help you solve some of these problems? Don't forget your calculus, practice every day, mimic test day conditions, and there's no reason you shouldn't pass. Talk to the instructor too. Sometimes he tells you pretty useful things to study, and it's in your capability. Maybe you see this test and think that all these are kind of straightforward problems. Maybe not, I don't know. But at least at the time, I can say that I wasn't really prepared to pass this test. But, okay, so I decided to do one of these problems, because I do have the solutions for them, and I think I'm going to do number 3. So let's do number 3. Where's my paper? I just had some paper here. Oh, here it is. And I do have a cheat sheet in case I get stuck. I tried doing it by memory before I started filming this video, just to see if I could remember it. And it didn't play out. I remembered most of it, but I got too scared, and I didn't want to screw up too much. I'd rather just show you how to do it. So I'm going to write down the things that I know. I always start there. And we want to prove something. Oh. All right. This problem has basically 3 tricks to it. And if you know the 3 tricks, then you're good. And the way we do it is that we essentially pass the buck off to a new sequence of functions, which is his first hint. So I define a sequence of functions gm to be the supremum of fn, where n is larger than or equal to m. So essentially we look at the biggest function, we define that to be g1, And then we start moving one up. Like, so for G2, we consider n bigger than or equal to 2. For m equal 3, we consider supremum over all functions where n is bigger than 3. So this sequence can only get smaller. Okay, so what do we know? We know that we know a few things. We know that Gm tends to 0 because the fn's tend to 0. And we know that Gm is bounded above by 1 for all m. What else do we know? Well, I don't have this written, but it is important to note. G1 is bigger than or equal to G2, bigger than or equal to G3. We know this. And because the Gn's are bigger than Fn's, so Fn is less than or equal to Gn, we know that the same is true for the maximal functions. Okay. Now what? We need to show the following claim. We claim that Mgn tends to 0, and that is enough to get the result. Which should make sense, right? Because if Mgn is bigger than Mfn, and if Mgm tends to 0, then Mfn will tend to 0, and then the proof the claim will be proven. How about that? Okay, so what do we do? Well, we know by Lebesgue's dominated convergence theorem, we know that the integral over the whole interval of Gn, we know that also has to tend to 0. So now we need to invoke the weak type 1-1 bound. So what does it mean? The weak type 1-1 type bound. What does it say? It says that the measure of Mgn bigger than alpha is less than or equal to some constant c. So this bound that I'm using here, this c is given. We don't actually have to find it. It's just afforded to us. So c over alpha integral 0 to 1 g n. I think it looks something like this. And now we are going to define a new set called E alpha to be the upper limit of Mgn bigger than alpha. And then what do we want to show with this set? What do we want to show with it? Okay, so if I call... Oh, I know what we're doing now. Then the measure, well, we'll write it this way. E alpha is less than or equal to c divided by alpha, integral 0 to 1 Gn. And this also tends to 0. How do I know that it tends to 0? Well, okay, what does it tend to 0 with is a bit better question. Does it tend to 0 with t, or does it tend to 0 with n? Because the integral of Gn's tends to 0. Oh, it tends to 0 with n. So you fixed the alpha, and you're letting n tend toward infinity. Okay, yeah, I got confused there for a second. Part of these videos is not to show you how to do it perfectly all the way through, because I think there's a lot of videos like that already. I think my goal with these videos that I'm making is to show that you are going to make a lot of mistakes, and I want to show you how important it is to work something out and then go, oh no, I messed up there, I need to correct that, because that's going to be like the typical experience, I think. I mean, I'm even looking at my notes over here, just trying to talk myself, because that's how you learn, right? Because it's not going to be obvious the first time you see it. Now, because I know this integral tends to 0, I know that since it's an upper bound for this guy, I know that the measure of E alpha has to be equal to 0. Which means what? It means that the set of all x such that the maximal function of Gn that do not tend to 0 is a subset of the union of 1 to infinity of E sub 1 over, and you know what, let's call these, no, I don't want to use n, let's call it k, 1 over k. So let me take a moment here just to explain what I've written. These EKs, the 1 over k, those are my alphas. So I'm picking these alphas and they're getting closer and closer to 0. And so this set where MGM does not tend to 0 has to be a subset, meaning that points in here are in these EKs, or these E1 over k somewhere. Because remember how E alpha was defined. E alpha is defined to be the upper limit of MGN is bigger than some positive number alpha. I don't think I mentioned alpha's positive here somewhere. I think I just kind of assumed it. So maybe I should make a note of that. So we'll put it here for alpha positive. You have this statement. Okay, now what? Because this set is a subset of all these guys, we notice that it has measure 0 because it's bounded above by this sequence here that tends to 0. So this set, which I guess if I want to call it, it really doesn't matter what I call it, so we'll call it we'll call it S for struggling grad student. Then the measure of the struggling grad student has to be equal to 0. And because this set has measure 0, that is by definition the set of all points where MGM does not tend to 0, which means that MGN has to tend to 0 almost everywhere, just by definition. And then we're done. Okay, so in the next 3 minutes, I think I would take a step back here, look at what is written, and see if I can make heads or tail of what's happening, because there's essentially 3 parts to this. So let's go back to the beginning. You have a sequence of Borel measurable functions. Everything's in the square. Fn tends to 0 almost everywhere. And we want to prove that the maximal functions of Fn tend to 0 almost everywhere as well. Okay, proof. The first thing you do is you define a new sequence of functions that kind of serve as an upper bound for this sequence of functions. That's why I'm letting it equal to supremum of Fn n bigger than m, which means that G1 will have to be bigger than G2, bigger than G3. And the reason they're in this order is because m is getting larger and larger and larger, so that you consider fewer and fewer f's. Okay. And because Gm is the supremum of Fn, I know that Fn is bounded above by Gn for every n, and by definition of the maximal function, we also preserve the inequality as well. And then we know some other things. We know that Gm has to tend to 0 because the Fn's tend to 0. That should be obvious. And Gm is bounded above by 1 because everything here is, in the unit square. So what does that tell me? It tells me that if I prove that the maximal functions of Gn tend to 0 almost everywhere, which I should probably write, almost everywhere, then I'll be done, because MGN bounds above MFN. Okay, that's trick number 1, this part here. Trick number 2 is identifying Lebesgue's dominated convergence theorem. By Lebesgue's dominated convergence theorem, I know that this integral tends to 0. That's just what that says. And now we use the hint that he gives us that we should invoke the weak 1-to-1 type bound. So for positive alpha, we know that the measure of this set is less than or equal to c divided by alpha times this integral. And then the idea here is that we know that this integral is tending to 0, so that the sets here have to be pretty small. So I define E alpha to be the upper limit MGN bigger than alpha. And then I essentially just rewrite it down here again. And that this sequence tends to 0 within. Well, within tending toward infinity. Which means that these E alphas are really small. They have 0 measure. And that these sets where MGM does not tend to 0 is a subset of these E alphas. And I've written the E alphas in a creative way. But all of these sets have measure 0. So because this set has measure 0, I know that MGM has to tend to 0 pretty much everywhere. Or in math language, almost everywhere. And since this is proved, the whole problem is proved. I don't know how long that took me, maybe 10 minutes, but when you're taking the test, you have to reconstruct all this, in a short amount of time. I knew that Lebesgue's dominated convergence theorem was involved here, but putting everything else together was, I guess, too much for me at the time. But now I have a trick, This part here, I wasn't really sure how to reconstruct. But now I know that this is in my tool belt, so in the future I might invoke something like this. Also, he did not tell us what the weak 1-1 type bound is on the test. I think he was expecting us to know that ourselves. So if you don't know what this is, you're kind of stuck. But I looked at it like the night before because he did tell us that the Hardy-Littlewood maximal function would be on the test. So like the night before, I read through the chapter on that in this book, the Stein book. Anyway, that's one problem from the test. I might do some more in the future. I know I'm going to do more problems in the future. But for now, I think that's good enough so you can get an idea of what kind of pacing that you should have when you take these tests. Anyway, thank you for watching my videos.